the lecture for today. Okay. Today we start to study about sequential circuit. Okay, the sequential circuit. There are two kinds of sequential circuit: synchronous and asynchronous sequential circuit. Okay. Okay. At first, for today, we learn about sequential synchronous sequential circuit first. For this circuit, the state of the circuit will change when the clock signal tick. Clock signal is used to determine the timing of state change. Okay. For example, I consider this signal of clock. This logic low, logic high, low, high. When clock change from low to high, okay, there are this edge. Sometimes it's called positive edge. If the state machine or sequential circuit change the state at this timing, it's called active high clock. But if the state change when clock change from high to low or at negative edge, this kind of state machine is called active low clock. Okay, and clock is high, low, high, right? Actually, you can just focus on only the edge. For example, only positive edge. You need not to consider logic high level or logic low level. Okay. Anyway, sometimes some circuit maybe must consider the length of logic high or logic low level. In this case, one parameter is called duty cycle or duty ratio. Namely, if this high level, for example, is half of one period, it's called 50% of duty cycle or duty ratio. So, now let's introduce the basic element that used in the system. This one. Okay, and sorry, I want to back. Okay, the element that goes to memory the state of the circuit. Okay, for this class, let's use this D flip-flop. Okay, is trigger D flip-flop. Okay, there is one clock terminal, one input, data input, and maybe one or two output. Output Q. For this output is active low output, namely the value of this, or sometimes it's called, in this case, Qn, or active low Q. Same thing, this one, or Qn. The value normally is opposite. For example, if Q is 0, Qn, negative of Q, will be 1. Or if Q is 1, Q in or active flow Q will be 1, this one will be 0. Okay, and the value of Q will be updated just only when clock tick, namely when the signal at clock terminal change from low to high. In this case, it is positive edge. Some flip-flop is active low. For active low, then we have inversion bubble right here. For this case, it change from high to low, okay, at negative edge. Okay, now let's consider the timing of change. It changes when clock tick. When clock tick. When clock tick, this flip-flop will read data from D. Okay. Read data from D. If the data is 0, then Q become 0. If data at input D is 1, when clock tick, Q change to 1. Okay. For constant level, low or high, nothing change. That means the value of present Q will be the same as the past or the last value of Q. Okay. For example, let's consider this clock. Okay, and this Q. When clock tick, flip-flop will read data from D. Now D is 1, right? Low, high. High is 1. Okay? Then Q change to 1. At here, into 1. There is some propagation delay. Okay? There is some delay time. And then after that, at high level, or at negative 8, or at low level, nothing change. Nothing change. Namely, any point of time during this, the value will be the same as the previous one or last Q. Okay, so in practical, you just consider only when clock tick. Okay, namely at here clock tick, D is 1, so Q change to 1. At here, when clock tick, input D is 0, right? So it changed to be 0. When clock tick at here and read data, now data at this timing is 0, then D is 0. Okay, and keep this value until next clock tick. When clock tick at here, D is 1, so Q update to 1. And clock tick at here, input D is 0, so output Q change to 0. Okay, everyone okay for this basic element we will use in signature circuit. Okay.
Sir?
Okay.
Hello, sir.
Okay. You can ask
Can
me.
you repeat again about clock is on, but x0 and x1. So D is x and 0 mean constant. So when D is x and clock T is 1, why is says like added low?
Mm-hmm.
Yeah.
Okay. At first, for it simple. Okay. This is clock, right? If there is no inversion bubble, that means it's positive edge ticker. Namely, the clock tick. In this case, you just consider when the signal change from low to high or at positive edge from low to high. For example, this one, when clock tick, the flip-flop, the D flip-flop will read data from input D. If it sees the value is 1, for example, at this point of time, the value of this one, right? Right? So the value
Yes.
of 1 from D will be read and update at Q. So now Q become 1 until next clock tick. For next clock tick, when clock tick, flip-flop read data from D again. Okay. At this point of time, input D is 0, right?
Yes.
So input D is 0. So it will update output Q with 0. So Q change to 0. Okay. And this point of time, clock tick, D is 0. So Q is 0. At this point of time, when clock tick, D is 1. That means when read data, Q then change to 1. And keep this value until next clock tick and read data again. Okay. When C is 0, then it becomes 0.
Okay, sir.
Okay. For active low, Q or QN, just opposite. Okay. Opposite value to Q. That's all. Okay, now.
Okay.
Okay, now. For clock synchronous state machine, the basic structure is this one. Okay. This one is flip-flop. Flip-flop to use as memory. For this class, let's use the flip-flop. The flip-flop. And there are more two combinational circuit, F and circuit E. Okay. Okay, now at first, let's focus on this part. This part is state memory. State memory. To memorize the state of the circuit. If you use only one flip-flop, that means output Q, there is only one output Q, right? Or only one bit of state variable. That means it can represent only two states. Namely when Q is 0 and when Q is 1. Okay. If your state memory use two flip-flop, something like this, D, Q, D, Q, and normally we use the same clock for all flip-flop. And this one may be Q1, Q2. So the value of flip-flop Q1, Q2 may be 0, 0, 0, 1, 1, 0, or 1, 1. Okay, so it can represent four situations. For example, for some traffic light, it may be this state maybe show the state of red, maybe green, something like that, or yellow. Okay, to represent the status of the circuit. For this state, at 0, 0, the circuit may produce the red. Sorry, let me draw repeat again at here. Assume this D Q clock. D Q clock. That this one is Q1, Q2, and this output of flip-flop will go to some circuit, and the output may be 3 lamps of red, green, yellow. Okay. And this clock. Okay, this is clock of the system. This circuit, this called circuit E, or output logic circuit. Output logic circuit. This circuit will convert the value from flip-flop to the final output of the circuit. For example, if the value of Q1, Q2 is 0, 0, you may design the circuit G to make lamp R or red turn on. Okay, and when it changes state to 0, 1, it may let green output turn on, or 1, 0 if input of output logic circuit or circuit G is 1, 0, it may decide to make 0 output turn on. Okay, everyone okay? Okay, so flip-flop it's just used for state memory. State memory. Okay, that will take state when clock tick. And the state value you can read from the value of Q1, Q2 or output of flip-flop. So Q1, Q2 or output of flip-flop, normally it is called state variable. State variable. Okay, state variable. Okay, to design, you might consider how many states of the system. For example, for this example, it's traffic light, and maybe they just red lamp turn on, output G turn on, output Y turn on. So there are 3 situations, right, of the output. So that means for 3 situations, it needs 2 bits, right? At least 2 bits to represent the state. So you should use at least 2 flip-flops for state memory. Okay, this is the point. And this because the output of flip-flop may be not to be the exact value of the output that you want. So it needs some some additional circuit to convert the state value to final output value. Okay, this circuit is called output logic, and normally this one is a combinational circuit. That we already learned from the past 2 days. Okay, you can use something like K-map for the designing tool. Okay, understand the concept? Okay, one more circuit. Okay, when clock tick, let's consider when clock tick, right? When clock tick, the flip-flop will read data from its input D, right? Where the input come from? Yes, it need more circuit, right? In this case, let's call circuit F. Circuit F will generate the value to input D. If F generates 0, 1, that means when clock tick, the flip-flop will read data 0, 1, right? And then update to Q1, Q2, then become 0, 1. Okay? And circuit G will convert or interpret the meaning of 0, 1 to the output, maybe green or yellow, something like that. So the circuit F then is named as next state logic. Next state logic, because the output of this circuit F will be the next state value of flip-flop. Okay, and the signal at here is called excitation signal. The output of flip-flop with excite or with input of the flip-flop is called excitation signal. Well, now the output of circuit F at first also combinational circuit. Okay, combinational circuit. Its input maybe come from external input, or maybe use input from flip-flop, okay, Q1, Q2 is possible. For example, input may be switched to if a name is as next or something like that. If the current state is 00, the red output turn on when clock tick, and input next is 1. So and now current state is 00. Input of F then is 1, 00. So F may be generate the next value maybe of 0, 1. So when clock tick, the flip-flop will read the data of 0, 1. So output update to 0, 1, and circuit G then produce the new output to make G turn on. Okay, it's just the main concept. So your the structure of clock synchronous state machine that we will study then composed with 3 main blocks, namely flip-flop that used for memorize the state, output logic T, and next state logic F. Okay, and there are, if you consider the output of the output logic T, and from the previous example of traffic light, its input is from flip-flop, right? That means when clock tick, flip-flop update the value, right? Maybe change to 0, 1. That means the input of circuit G update also. And don't forget that circuit G is combinational circuit. That means if the input change the value, the output of the circuit will be changed suddenly with some propagation delay. Okay, namely the output also change at the same timing of clock. Understand? Clock tick, flip-flop generate new value. The new value is the input of G. That means circuit G will update its output, follow the new value of its inputs. That means the output will change at the same timing of clock. Okay. This kind of state machine is called Moore machine. The next type of state machine is mirroring machine. For mirroring machine, the circuit G, output logic G, of course, it get input from flip-flop that change when clock tick, and it get input from external input. That means when clock tick, flip-flop change the value, circuit G produce the new value. Okay, and output may be changed when this input change also, right? When input change, then output may be changed. That means this kind of state machine, the output may be changed when clock tick or when input change the value. Okay, this is mirror type state machine. Maybe this T it function both state variable and external input variable. Compare with Moore machine. For Moore machine, circuit T is only function of state variable, namely Q1, Q2. Okay, so now let's start to analyze.
Hello, sir.
Okay,
Can you repeat the last explanation again because the connection lag? Sorry.
okay. The difference, okay, between Moore machine and mirror machine is that uh, the output logic G circuit. For Moore machine, it receives the input from output of flip-flop or state variable Q1, Q2, for example. That means when clock tick, flip-flop update its value, right? Right? Q1, Q2 change. That means input of G change also. So output then change. Okay? Because G is combinational circuit. If some input change, it can make output change suddenly. Okay, so output then change at the same timing of clock. But for mirror type state machine, it gets input from external input also. So the output may be changed when external input change the value. That means output may be changed at the same timing of clock or when some external input change. Okay?
So then, can we also call the output logic G as a combination circuit?
Yes, yes.
Still,
Output circuit G is combinational circuit, which will change the output when some input change. Okay, let's see example. Okay, example number 1. For this state machine, there are two flip-flops which use the same clock. So it is synchronized together. When clock tick, flip-flop will read data from, in this case, D0 and D1 at the same time. This part of circuit is circuit F, next state logic. This circuit is output logic G that used to convert, okay, state and maybe use some external input. En is, in this case, is the external input. So the output max, name of the output max, is then the function of Q1, Q0, and input n, En. Namely, if you write equation, because this one is AND gate, so max is Q0 and Q1 and En. So it functions both state variable Q1, Q0 and external input En. So this is mirror type state machine. Okay. And now let's analyze this circuit. To analyze the circuit for combinatorial circuit, normally we want to know how the output relate with the input, right? But for state machine, of course, you need to know the output value, right? delay with something, right? But that's not enough. For a state machine, you need to know also that when clock tick, what is the new value of Q1, Q0, or what is the next state value? Okay, next state. Oops, sorry. Next state. Okay, you need to determine the next state. Okay. Okay, let's see example. For this example, the output max equal to Q1 and Q0 and input EN. So it's called output equation. And from flip-flop, for D flip-flop, the value of Q, the new value of Q, let's say Q star, the new value of output of flip-flop after clock tick. Okay, Q star. Okay, for Q0, it read data from D. So write Q star equal to D. This one also Q1 star equal to D1. Okay. The relationship between the output and input of flip-flop is called excitation equation. Characteristic equation. And the value of D that relate with external input or state variable that feedback to the circuit F is called excitation equation. Okay, because D is excitation signal. So from this circuit diagram, D0 equal to the signal and this signal all together, and this one it form back to this page for the bigger one. Okay, and this one is AND between Q0 prime and input EN, and this one is Q0 and EN prime. So then D0 is Q0 EN prime plus Q0 prime EN. For D1 also, okay, you can derive from this circuit connection, and you get this one. Okay, this is excitation equation. We show the relationship between output of flip-flop that feed to D flip-flop. That output of circuit F that feed to flip-flop. Okay, in this case, two flip-flop. Okay, this is D0, D1. Relate with what? With the input of circuit F, which is EN, Q0, and Q1. Q0, Q1 feedback from output of the flip-flop. Okay? Okay? And don't forget that circuit F is also combinatorial circuit. And if you substitute the value of D to this equation, so you get that Q star equal to something about Q0 EN or Q1. And this is called transition equation, state transition equation. Because this equation can show you that when clock tick, what is the new value of state. For example, if the current state or present state Q1, Q0 is 0, 0. So it's 0, 0, right? 0 prime, 0, 0 prime, 0, 0, 0 prime. And if external input is 1, so it's 1. 1 prime, something like that. 1, 1. That means the output of circuit F when input now is En is 1, Q1, Q0 is 0. So the output of circuit F will generate D0, D1 as what? 0, 0. This is 1, right? For this term is 0 at here, 0 at here, 0 at here. Okay, becomes 0. Okay. This circuit F generate output of 1, 0 at here. Okay. Now the value of Q0, Q1 is 0, 0, right? Okay. And when clock tick, flip-flop update its data from input D, right? So the new value of flip-flop then become what? 1, 0. Okay. It changed to 1, 0. Okay. Okay. So this is the new value of flip-flop. Q0 star, Q1 star. Okay. Understand the meaning? So from state equation, you can summarize in the table. For example, I write state variable at this column and input value at this header, and the value of Q1 star, Q0 star, I will fill in this table. So you just substitute all possible value, right? For example, when Q1, Q0 is 0, 0, En is 0, you just substitute and calculate the value. Then we know the value of Q0 star and Q1 star. Okay, you can do. Or to make it faster, you may consider, for example, as you know from the previous lecture, this Q0 star will be 1 if you consider in the value of 1 when this term is 1, right? Or this term is 1, right? This term will be 1 when Q0 is 1, En is 0, right? So you just find out the column or row when Q0 is 1 at here and En is 0. So Q0 star at this and this is 1, 1. Or this term is 1. When Q0 is 0, En is 1. Q0 is 0, En is 1. Okay, so this one. So Q0 star will be 1 for this 4 condition. Okay, and another cell then becomes 0. For Q1 star also, you can consider the condition that will make the value become 1 because this is sum of product term, right? So it's very easy. This term will be 1 when Q1 is 1, En is 0. Q1 is 1, En is 0. So it's 1, 1 at here. For this term is 0, 1, 1. For Q1, Q0, 0, 1, and En. So it's 1 at here. And the last one, 1, 0, 1, 1, 0, 1. Okay, this value. And another value of Q1 star, 0. Okay, you can consider or fill the table by this technique. Maybe faster than substitute for every possible value of Q1, Q0, and En.
Sir, sorry, can you repeat explanation again? The transition table.
Okay, from this equation, right? if you know the value of Q1, Q0 and En, right? You can calculate the value of Q0 star and Q1 star, the new value when of flip-flop when clock tick. Okay, so because there are 1, 2, 3, right? Three, three, 3-bit, right? So there are 8 possibility, right? Right. So you must
Yes.
calculate all these 8 possibility, all of them, by substitute the value to these two equations to calculate Q0 star and Q1 star to complete this table. Okay?
Okay.
Okay. Anyway, it takes time, right?
Hello, sir.
So it takes time, right? If you substitute for every case from this 8 possibility. So I just show you some technique you can consider by the question that make this term become 1. For example, this one will be 1 when this term is 1, right? This term will be 1 when Q0 is 1 and input En is 0, right? So you find out when Q0 is 1 at here, and En is 0. Okay, that means the value of Q0 star, this digit, is 1, 1 at here. And for this one also, 0, 1, right? 0 at here, 1 at here, so 1, 1 at here. For another value 0, like K-map.
Yes.
Okay?
Okay.
Okay. So this is called transition table. And sometimes, for more convenient, you may naming this state. For example, for traffic light, you may name this state as red, this value as state green, this value may be state yellow, something like that. Anyway, for this example, I just name it as A, B, C, and D. Okay, state A mean the value of Q1, Q0 is 0, 0. State B mean the value of state variable 0, 1. C, Q1, Q0 is 1, 0. D is 1, 1. That means this is 0, 0, 0, 0 mean state A, right? So write A at here. 0, 1 means state B, then write B at here. Okay, and so on. So you get new table. Let's call state table. Same thing. This just write in binary value. This write in the name of the state. Okay.
Hello, sir. What is the EN stand for?
Mm-hmm. Yeah.
Yeah.
Okay.
What is the EN stand for?
What is what? State.
What is the EN stand for?
Yeah. This state, right? State A stands for 0, 0. The value of flip-flop Q1, Q0 when it becomes 0, 0. Let's call it state A. For some application, for example, traffic light, you may define as red, something like that. Red, green, yellow. Based on the application. For the example, just general, then I call it as A, B, C, and D. No any meaning. Okay. Now let consider this transition table or state table. Assume how to use this one. Assume this is D flip-flop, right? D flip-flop and output Q0, Q0, Q1. Okay. If you know that now the current state, the value of Q1, Q0 is 0, 0, is 0, 0, And when clock tick, you know that when clock tick, the value of input is 1. That means the next state or the new value of Q1 star, Q0 star, then it's become 0, 1, right? From this table. Or when the machine is on state A, when clock tick, input is 1, then change to state B. Understand?
Yes, yes.
Okay, that shows that when clock tick, what is the new state? Okay, this is a function of this state table or transition table. Okay, you can determine the next state easily by looking from this table. Okay, more convenient than using this equation. Okay, because you know the value suddenly. Okay, by the way, for the output equation also depend on Q1, Q0, right? Namely Q1, Q0 when it's 0, 0, 0, 1, 1, 0, and 1. Sorry, 1, 0, and 1, 1. Okay, the output will be 1 when what? When it's on state 1, 1, right? And input in is 1, right? That means on state 1, 1, 1, 1, in this case is state D, right? State D. And when input is 1, output is 1. For another case, output are 0. Okay, that's all. So you can get this table, which called output table, to show the output. If you know that, for example, if you know that the current state is state D, and you know that now input value is 1, so you can know the output suddenly by looking from this output table. Okay? Okay? And because this state table and this output table, the header of the table are the same, so to write more compact table, compact form, sometimes we write all of them together. Okay, same header. For this column is next state, and this column is output. Okay, to make it more compact. Okay, now from state output table, sometimes you may write it's a state diagram. Okay, to make it more easy to understand the movement, okay, or the state change, something like this. Okay, okay. At first, back. At first, we write all state. In this case, state A, B, C, and D, right? Write all of them, and 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 consider what is the next state. For example, now at state A, when clock tick, if input is 0, the next state then is A, right? So write something like this. From A to A, when input is 0. And at state A, when input is 1, go to state B, when input is 1. Okay? Now I just consider the next state only. At state B, when input is 0, go to state B. Right? When EN is 0, But when input is 1, change from B to C. Change from B to C when input is 1. Okay, and so on. Now, if you consider the output at state A, when input is 0, output is 0. Okay, you can write output max is 0. Okay, near the arc, okay, and the arrow. So finally, if you do all of this, you can get this state diagram. Okay, so from this state diagram it's easy, right? If you know that now it's state A when input is 1, so when clock tick it change to state B, and if it's on state B when clock tick, if input is 0, it still be on state B. When clock tick, now input change to 1, it go to state C. If the current state is C, when clock tick, input is 1, go to state D, something like this. Okay, you can know the next state suddenly by looking on this state diagram. And you want to know the output, maybe now if circuit is on state D and input is 0, so output is 0. But when input change to 1, output max change to 1. Okay, so you can know the information of next state and output from this state diagram also. Okay, someone prefer this one, someone prefer this one. Okay, which one is okay? Okay, now, okay, after that you may check. Okay, maybe check, for example, if you want to know the output value, if it start from state A, when clock tick, start from state A, when clock tick, En is 0, right? From this one, when input is 0, the next state is A. That means from this point of time to this point of time, the machine is on state A until next clock tick. Next clock tick, input is 0, go to A, right? And keep this state until next clock tick. Okay, for next clock tick, input En is 1, right? En is 1, go to state B, right? So from this point of time, change to state B until next clock tick. Input is 1, change to C. Okay. At this clock tick, input is 0. Okay, nothing changed, still be state C. This clock tick, input is 0, nothing changed, still be state C. At this clock tick, input is 1, change from C to D, right? Input is 1. At this clock tick, input is 0, still be on state D, and so on. Understand? You should know the state, okay, for each period of clock. After that, if you want to know the output, okay, you can consider easily. For example, this example, output is 1, right? Only one case when it's on state D and input is 1. So you find state D, right? And when input is 1 at here, here, and here. So output max is 1 at here. For another period of time, output is 0. So the output of the circuit then become this, like this timing diagram. Okay, for analyze. And for this example and similar circuit, if I delete this wire, that connect between input to this AND gate. That means now the output not depend on input EN, but depend only Q0 and Q1 from flip-flop. So output then is function only state variable. Then it's become more machine. Okay. In this case, I change the name of the output to max. Okay. To analyze it's the same. Okay, the same. Okay, same state and transition equation, just different at the output equation. And because the output based on only state variable, so you can write the output with this style, namely at state A output is 0, at state B output is 0, at state C output is 0, at state D output is 1. Depend on only state, not depend on input value. Okay, if you write in the previous style something like this, if you change condition to max, okay, max equal to Q0 and Q1, so by the result this is BB1, so it's the same, right? 0 0 0 1 0 0 0 1. So you can separate this column for the output max. Okay, in the case of more type state machine. And for state diagram, okay, you can write the output inside the circle of the state.
Sir, excuse me, sir. Can you repeat the explanation again? Your connection lagged.
Now I disconnect, right? Disconnect the input from external input, right? Disconnect, that connect to this AND gate. That means your function, output function now is just Q0 and Q1, right? Depend on only state variable, namely the output value depend on only state, not depend on input value, right? So I just separate the column of output at here. That's all. So in state diagram, so I write the value of output inside this state circle to show that output value depend on state only. Namely, if circuit is on state A, output is 0. If the circuit is state D, output then is 1. That's all. So from the previous example, if input change, okay, and if you know the state for each period of time, you can determine the value of output, right? Because output will be 1 when the circuit is on state D, so it's 1 at here. Another period of time, output 0. Okay, compare with this case and this case, it's different, right? This mirror type state machine and this one is more machine. For mirror type, output may be changed when input change, but for more type state machine, output will change when clock tick only.
Sir, so how about enable? Like on the state diagram, it's say some of the value and enable is 0, enable is 1, move to B. So how about that outside of the cycle?
Same thing, right? Same thing. For example, at state A, right? When clock tick and input EN is 1, so it's go to state B. For this example, it's the same circuit, right? this example, this circuit, this circuit and this circuit are the same thing. This part of the circuit F exactly the same. I just delete this wire that connect between external input and this AND gate only. Okay, for this example, to compare
Okay, so
different.
in Melee machine, we put the output max outside of the circuit because that it depends on both on anywhere and state outputs.
Mhm,
For for mode, we just import only output inside of the cycle.
mhm.
Okay. Okay,
Okay,
so
for next example, and for this example, there are 1, 2, 3, right? 3 flip-flop. So there are 3 state variable. In this case, it's Q2, Q1, and Q0. So there are uh, 8 state, right? 8 state. Namely, when Q1, Q2, Q2, Q1, Q0, the value is 0, 0, 0, 0, 0, 1 until 1, 1, 1. Okay, there are 8 states. 8 states. And from this one, this is the output circuit G. We get the data from Q2 and Q1, right? And this one Q function of Q2 and Q0. For this one is from Q0 directly. This is from Q1 and input of Q2. So the output equation of this one is the function of only state variable. So this is multi-type state machine. Okay, and from this part of the circuit, you can determine the uh, excitation equation and then transition equation. When you convert to uh, transition table, you can write something like this. And when you name for each state value, you can name, for example, A, B, C, D, F, G, and then H. Okay. And when you write state diagram, the point is this one. When you write state diagram, for example, when you change from state A, when input is 1, 0, change from A to B, right? If input is 1, 1, change from A to B also. Okay. If you write at X, Y is 1, 0, X, Y is 1, 1. So you must write a lot of arrow, right, or arc. Okay. So to reduce number of line in the diagram, we can use uh, the technique something like the previous lecture. For example, A we change to state B. This case when x is 1, y is 0, or x is 1, y is 1. That means if x is 1, we will change from A to B, right? So you can write this condition by variable x, right? Okay, that means if the input xy make this condition become true. For example, if input xy is 1, 0, x is 1, condition become true, right? So when clock tick, we change from A to B. But if input is 0, 1, now x is 0, x is 0, not true, right? So when clock tick is not follow this direction. Okay. Or for example, from A to E. is 0, 1, right? You can write is an x prime y, because this term will be 1 or become true only when x is 0, y is 1. Okay. For this expression, then it's called transition expression. And for E to F, okay, every case of input, okay, when circuit at state E is equal to F for every possible input. That means it's not depend on X and Y. It's just wait for clock tick. Okay, I write 1. That means it's always 2. Just wait for clock tick to change the state E to F. Okay. That means you can write in this style: input value to input variable equal to some value, or write in this transition expression style.
Sir, can you please explain a little bit about transition output table on the left side?
This one,
No, left side. Left.
left side, yes.
Yeah, yes.
From this one, is come from this set of equation for this part, and for the output value, it from this equation by substitute all possible value, or consider when it will be 1. Okay, bit by bit. For example, output Z1 will be 1 when Q2 is 1, or Q1 is 0, Q0 is 0, right? So Q2 is 1, Q2 is 1, this 1, 1, 1, 1, right? So it's 1, 1, 1, 1 at here. Or Q1 is 0, Q1 is 0 at here, here, right? So it's 1, 1 at here. Or Q0 is 0, Q0 is 0 at here, 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 here. So then it's become 1 at here also. Something like that. From equation, you can produce this state transition output table. When you get this one, if you know the current state, for example, is 0, 0, when clock tick, you know that input value is 1, 0. That means it will change to state of 0, 0, 1. Namely, the value of flip-flop Q2, Q1, Q0 will change to change from 0, 0 to 0, 0, 1 when clock tick. Okay. Okay, just summarize. Okay, now if you understand, now let's do some design. Okay, previously it's analyzed for this side circuit. From the problem, you should draw this state diagram or this state output table. After that, you convert to transition output table, and then from this one, you can derive equation for circuit F and circuit G. If you know circuit F and circuit G, that means you can implement the circuit completely. Okay, at reverse process. Okay, analyze and synthesis. Okay, so let's see example. Example 1. Example 1. Let's design clock synchronous state machine with two input A, B. Okay, the circuit may be something like this. There are two input A, B, and one output Z. Okay, the output Z is 1 if there are two conditions. Okay, if A had the same value at each of two previous clock tick, or something at first condition. A had the same value at each of two previous clock tick. For example, at this point of time, the previous clock tick at this point of time, two previous clock tick is this one and something. Okay, but now there is no the previous clock, so condition is not true, right? It will be true maybe at this point of time. At this point of time, the two previous clock tick is this one and this one, right? At this one, A is 0. At this one, A is 0. Two previous clock tick, A had the same value, so output become 1. This one also. Two previous clock tick, here and here, right? So let consider from at the beginning. At the beginning, assume output Z is 0, okay? Because there is no any clock tick at the beginning. Clock tick for the first clock tick, this condition still be not true. That means output still be 0, right? And when clock tick now, the previous one is 0, right? At this time is 0, right? That means after this point of time, the two previous clock tick at here and at here, this condition become true, right? So the output then become 1 until next clock tick. When clock tick now is 1, right? At this point of time, or this after this clock tick, the previous two clock tick here and here, right? A is 0, A is 1 are not the same. Okay, this condition is not true, so output back to 0. Okay, even okay for the first condition for this example. And for this clock tick, A is 1, right? The previous one is 1, same, right? So output Z then become 1. For the next clock tick, A now is 0, but the previous one is 1, so it's different. So output Z then becomes 0. At this clock tick, input A is 0, previous one is 0 also. So same, right? So after this clock tick, then output Z become 1. Okay, this is the first condition. The second condition, output Z will be 1 when B has been 1. Since the last time the first condition was true, this is mean when output Z is 1 and B is 1, the output still be 1. For example, in this case, when clock tick at here, now output Z is 1, right? And B is 1. So you cannot consider the value of A. By this condition, the output Z still be 1. Okay, clock tick at here, B is 1 and output Z is 1, so output still be 1. This is the second condition. But when clock tick at here, now B is 0. The second condition is not true, so you must consider the first condition, right? For the first condition, now A is 0, the previous is 0, okay? Different, so output become 0. At this clock tick, B is 1, but output Z is not 1, so you must use first condition by consider value A A is 1 1, so output become 1. At this clock tick, B 0, A is 0. So use first condition 1 0, so output becomes 0. Okay? Okay, to do the design, at first you must know how many states of uh, the problem of from this problem. If you don't know number of states, so you cannot determine number of flip-flop, right? So if you don't know, you can uh, uh, assume, okay, or generate the state. For example, like this one. Okay, for this example, okay, for the example, I generate state, initial state, For initial state, uh, output output is 0, and the state A0, output is 0, and the previous value of A is 0. A1 is the state that output is 0, and the last input value of A at clock tick is 1. OK0, output is 1, and the last value of A is 0. OK1 is 1, output is 1, and the last value of input A is 1. After that, I just consider what is the next state. For example, at the initial, if input AB is 0, 0, namely A is 0, that means it should go to A0, right? Go to the state that output is 0 and the last value of A at clock tick is 0. Right? So next state then is 0. But at initial state, if input A is 1, so it go to A1. And at state A0, output is 0, and the last value of A is 0. That means if clock tick and input A is 0, that means now A is 0 and clock tick A is 0 again. It should go to the state that output to be 1, right? And in this case, I define OK0 is the state that output is 0 and the last value of A is 0. Okay, at A0, the previous value of the last value of A is 0. If input A is 1, so it's not the same, right? It must go to the state that output is 0 and the last value of A is 1. So it's go to A1. Okay, something like this. Okay, you can complete this state table. Okay, for the example, you may not understand the detail. It's okay. I just show you some process for the design. Okay, someone maybe assume the condition different. For example, someone may get 1, 2, 3, 4, 5, 6, 7 state. Someone may make the state table with 9 state. Okay, it's okay. It's okay. It's okay. All okay if it work. Anyway, if for example, if you use this state table, that means 9 state. For 9 state, how many flip-flop need? at least 2 flip-flop not enough, right? 3 not enough, right? Because 3 flip-flop it can represent only 8, right? You must use what? 4 flip-flop or 4 state variable, okay? That can represent 9 state. But if you can reduce to, for example, you can reduce to 5 state. That means you can use only 3 bit or 3 flip-flop, right? Okay. So at the beginning, don't worry about that. It's minimal state, number of state or not. Okay, you can do and complete all of this. But when you complete this one, so you must consider is there some equivalent state or not? What is equivalent state? Equivalent state means the state that have the same output and the same next state for any input. Okay. For example, look on this one. For OKA1, the next state of input AB when input AB is 0, 0 is A0, right? And when input AB is 0, 1, next state is this 1, 1. The next state is OK1, 1. This one, OK1, 1. Output of this state is 1. This state and this state, OK1, 1. OK1, 1 also have got the same next state and the same output. So these two states are equivalent. Okay, you can remove one of them. Okay, for state OK0, 0 and OKA0 also, right? Same next state and same output. So you can delete. Okay, one. So finally you have got 5 states. Okay, for this one also. Okay, for this example, this state and this state are equivalent together, namely same output and same next state for all possible input value. So you can reduce, okay, by adding this to this, namely AE10. You can change to A110. Okay, that means AE10 at here. Don't forget to change the name. A110, okay, and so on. For this one also, you can reduce, okay, this to this. Okay, so finally you get 5 steps, okay, for the final result. So if possible, don't forget to do step minimization. Okay, in general, you can do state minimization by the technique of partition procedure. Okay, by this one. Okay, it said that for definition one, just say that two states are equivalent when it have got the same output at the same next state. And for definition number 2, it said that the partition consists of one or more blocks, where each block comprises a subset of states that may be different, may be equivalent. Okay, keyword is maybe. If you don't know, but if it's possible to be equivalent, let's group it together. But the state in the given block are definitely not equivalent. Okay, will be separate together. Okay, let's see example. If you have got state table something like this, This is the present state or current state. A, B, C, D, F, G. And next state, when input W is 0 and input W is 1. And this is the output for each state. At state A, output is 1. At state B, output is 1. At state C, output is 0. At state D, output is 1. State E, F, G, output 0. Okay? Now, let's do partition. At the beginning, I group all of them together because it's possible all of them may be the same, all of them are equivalent together. But if I, for example, if I consider the output 1, 1, 1, state A, state B, and state D give the output of logic 1, but C, E, F, G, its output is 0, right? That means A, B, D cannot equivalent to C or E or F or G, right? Because it have got different output value, right? Equivalent state must have the same output, but now it's different. So I can separate A, B, D from C, E, F, G. Okay? That's the point. Even okay? From step P1 to P2. Okay? Now, if I consider this group C, E, F, G, C, E, F, G, which have logic 0 output. Now let's consider next step. When input is 0, next step is F. F is in this group, right? Next step is F. F is in this group. Next step of F is E. E is in this group. Next step of this F in this group. It's okay, right? Till now. But when input is 1, next state of C is E. E in this group. Next state of E is C. C in this group, still be okay, right? Same group, right? F is D. Oh, D is in this group. Okay? And G is G in this group. You can note that this one. Next state of F, when input W is 1, is D. Okay, but another next state is in this group. But for F, when input W is 1, are this it's in this group. But
Sir, can you please repeat again because your connection lagged again?
Okay, from this to this is okay, right? Now I just consider in this group C, E, F, G, state C, E, F, G. Okay, when input W is 1, you can note that the next state of C is E, next state of E is C, next state of G is G. E, C, G are in the same group, right? The same block. Okay, but next state of F is D. D is in this group, and you already know that the state in this group and this group are not equivalent. That means this next state, okay, and this next state are different. So state F then not equivalent to C, E, G. So you can separate, okay, or do the partition F from this group. Okay. And if I consider A, B, D, A, B, D, which give logic 1 output. Again, if I consider the view is 0, next state is B, D, B. B, D, B, same group is okay, but when the view is 1, A, B, D, C, F, G, C, F, G, this F, right? The next state F is not equivalent to C and G, right? That means B is not equivalent to A and D also, right? Because equivalent state must have the same next state, but these next state are not equivalent, so B cannot equivalent to A and D. So I separate B from this group. Okay. After that, if you consider AD, next state is B, next state is CG. CG in the same group, right? It's possible to be equivalent, okay? And same output, okay? It's to be possible to be equivalent, okay? And B only one is okay. CEG, CEG. Next state is F, FF, okay? Same. E, E, C, E. ECG in the same group, right? And same output. That means it's to be possible to be equivalent, okay? Okay, so you can see that this step, you get the same result. Okay, that means A equivalent to D, B and C, E, G equivalent together. So finally, you have got 1, 2, 3, 4, 4 states. Okay, and you can select one of these. Okay, for example, A, D, then I change D to A, right? Or you can delete this one. Okay, left only A and B and C. So you need to write E and G, right? Because it's equivalent together. And then F. Okay? So you can minimize the state by using this partitioning method.
Sorry. How did you like delete C D E G? So we got the final state in 1, 2, 3, 4 P4 four states, and then yeah, after that, can you
P4,
again? Yeah.
if you consider from P4 to P5,
Yes, it is okay, and P5 to the final result P4 is also okay, but the latest step.
so if you do that and P5 and P4 are the same, that means you cannot do more partitioning, right? That's all. You can stop. When you stop, there are 1, 2, 3, 4, right? 4 groups. That means there are 4 states. Okay. For this one, you can use A or D, right? I select A and delete D because it's equivalent together, right? You can remove one. Okay. And B, okay, only single state. C, E, G, you can remove two of uh, them. In this case, I remove
Okay.
E and G because I left one equivalent state at C. Okay, that's all. Okay, more example. For this example, the next state of S1 to S9 when input D in 2-bit input is 0, 0, 0, 1, 1, 0, and 1, 1 as this table and output Z. For this means unspecified. Okay, don't specify the next state of S1 when input is 1, 1. Okay, in this case, you can do partition also at the same method. For example, at the beginning, again, I group all of them together. Assume it's to be possible to equivalent together. But if I consider the output value, okay, is 4, is 5, is 7, 8, and 9, give logic 1 output, that means you can separate, okay, 4, 5, 7, 8, 9, okay, from 1, 2, 3, 6, okay, by consider the output value, okay. After that, if I consider this group from the next state, S1, S2, S3, and 6, and the next state when input is 0, 0 is 1, 2, 3, 6, 1, 2, 3, 6, it's the same group, right? Okay, it's to be okay. But when consider the next input, next state is 3, 4, 6, 8, 3, 4, 6, 8. 4, 8 is different from not equivalent, right, to S3 and X6, right? So you must separate 4 and 8, namely state S2 and S6, right, from S1, S2. Okay, separate it. Okay, and for S now S1, S3. If you S1, S3 for this output is S2, S7. S2 in this group, S7 is this group. Okay, different. So you can separate S1 from S3. Okay, and from P3 to P4, you consider this set of state that give logic 1 output, right? 4, 5, 7, 8, 9. What is the next state? 1, 3, 1, 1, 3. But 1, 3 are not equivalent together, right? So you must separate this S4, 1 at here, 1 at here, 4, 7, 8, right? To one group, and 5, 9, we have S3 as the next state for more group. Okay, and after that, if I consider S2, S6, S2, S6, next state is 2, 3, sorry, 2 and 6, next state is 2, 6, 2, 6 in the same group, right? 4, 8, 4, 8 in the same group, 5, 9, 4, 9 in the same group. So it's still be possible to be equivalent together, right? So you can keep this group member. And 4 is 4, 7, 8 is 4, 7, 8. The next state for this input is 1, 1, 1. Okay, the same. And the left is unspecified. So it's to be possible, okay, to be equivalent state. And for S5 and S9, 5 and 9, next state is S3, right? And same output. So that means you cannot reduce more. So there are 1, 2, 3, 4, 5 group of 5 equivalent state. Okay, 5 state finally.
So can you repeat again from P2 to P3 state?
2 to 3.
Yes.
I just consider this group, right? Now it's 1, 2, 3, 6, right? It is the same output, right? So I just consider the next state. For example, is 1, is 2 is 3 and 6, right? The next state when input is 0 0 is 1 2 3 6. Let's check.
Okay.
1 2 3 6. The same group. Okay. For now it's no problem, right? For the input, right? But you must take all possible input. 1 2 3 6. This case, next state of S1 when input is 0 1 is 3, is 4, is 6, and is 7. 3, 4,
Oh,
right? Different, right? Right? 3, 4 is 6 and 8. Okay. That means for S, next state is S4 and S8. S2 and S6 must separate from S1 and 2, right?
yes.
Right? And sorry, 1 and 3, right?
Mm-hmm.
Right? And if I consider in the case input is 1 0, 1 0, for 1 0, next state is S2, is 5 7 9, 2 5 7 9. In this case, next state is S2, so S1 is not equivalent to this group, right?
Yes.
So you should separate S1 from this. Okay, so S2 S6, okay, separate from this group, S1 also. So you can generate these three. Okay.
Yes.
Okay. Okay. Next step. After after you get after you get state table, so you may, for example, you may assign binary value for each state name. Okay. For example, you may define it as 0 0 0 1 1 0 1 0 0 1 1 and 1 0 0 for this state, or use this one. Anything is okay. That's different binary code is okay, right? Different value is okay. For this example, I use this one for this state name. Okay, namely, if it's 0 0 0 is initial state. Okay, and for 1 0 0 1 0 1 for state A0 and A1 respectively, and 1 1 0 1 1 1 is for OK0 and OK1. Okay, note I use this one because the value of Q3 is corresponding to the value of input A at the last clock tick. Okay. Anyway, you can use anything. Okay. So after that, when I do this, and sometimes it's called state assignment. Okay, to assign the value to each state name. Okay, this is state assignment. And after that, I replace each name of state by this binary value. So then I will get this table, right? Transition table. And in this case, there are three state variables, Q1, Q2, and Q3. After that, I just select flip-flop. And for this example, I use D flip-flop. Okay, if I use D flip-flop, so what happened? For D flip-flop, for D flip-flop, D flip-flop, when clock tick, the new value of Q or Q star are the same value of D, right? Right? If D is 0, then Q star becomes 0. if this one Q star become 1. That means I just copy the value of this of Q star to this table of value of D or excitation signal. Okay. Anyway, for this example, there are 3 bits of state variable which can represent from 00 to 111. But now we use only 5 states, right? For the code of 001, 010, and 011 are not used or become unused state. The problem is what is the output of this state, or what is the next state of this state? Because it's possible, right? If the machine is on this state, when clock tick, what is the next state? This is the problem. For example, 1, 2, 3, 4, 5. This is used state and unused state. 1, 2, 3, right? When clock tick, maybe something like this. Just for example, for normal operating, the state should be rotate within this normal state. Okay, this is normal state. Okay, but this one is unused, right? It's something occur if the state lost to one of these unused state. So what happened? If the next state of unused state can back to some normal state, it's okay, right? You just wait for 1 or 2 clock tick, then it can back to the normal operation. But what happened if your next state of unused state is something like this, not back to the normal group, not back to the normal state? What happened? The machine or the circuit cannot back to the normal operation, right? Something like when you use a computer or your smartphone, sometimes it freeze, right? Or hang, right? You cannot do nothing. You must restart. Okay? This is the situation. If the next state of unused state is unused state. Okay? So to prevent this problem, you should define the next state of unused state. Okay? For safety, or sometimes it's called minimal risk. Okay? To reduce and minimize the risk. Sometimes we define the next state for unused state to be some normal state. Okay? This is called minimal risk. But someone want to minimize the size of the circuit. Someone not define the next state of unused state at the beginning, but let the next state of unused state is don't care. Go to some don't care. And when you decide by using something like K-map, okay, to minimize or reduce number of variables. After that, you just check that the next state of unused state can back to the normal state or not. Okay, this is called minimal cost. Okay, minimal cost. Okay, so for this example, I will show you two of them. For minimalist, in this case, I define next state of unused state to be 0, 0, 0. That means output is 0, 0, 0, 0, 0, 0. or back to the initial state. This is minimal risk. Okay, if you see in K-map, this one is 0. But for minimal cost, okay, I treat it as don't care at the beginning. Okay, so when you use K-map, I just try to select as big as possible for each group. So, and from K-map, okay, you can get the equation. This is for minimal risk, this is for minimal cost. So from this set of equation, that means now you know the circuit of F, right? Namely, output of circuit F is D1, D2, D3, right? And its input maybe come from output of flip-flop Q1, Q2, Q3, and external input, right? In this case, external input is AB. So you can implement or draw the circuit diagram of F from this equation. Okay, input A, B, and feedback from Q1, Q2, and Q3. Output of circuit F is D1, D2, D3 that feed to the flip-flop. And for output equation, also you can derive from this. Okay, from this one. Maybe someone define output of unused state as 0, 0, or you may treat it as don't care also. Okay, so if you use minimal risk, define the output to be 0, you get equation like this. But for minimal cost, your output equation is this one. So from this output equation, you can draw the circuit diagram of G, okay, that produce output Z, and get the input from Q1, Q2, and Q3. Okay, and for example, for minimal cost, okay, it this one. This is flip-flop, right? 3 flip-flop. This is circuit F. Okay, and circuit G in this case have nothing because I show you for minimal cost. Output Z equal to Q2. So I can take the signal from Q2 directly to be the output. Okay, that's all for the design. Okay, another example. For this example, okay, I will show you shortly. For this example, let's design binary count up down binary up down counter to count from 0, 1, 2, 3, 0, 1, 2, 3, count up. Okay, 1, 2, 3, and repeat 0, 1, 2, 3. And count down when C is 1, input C is 1, 3, 2, 1, 0, 3, 2, 1, 0. From the problem, you may write the state output table like this. When C is 0, count up, may change from S2 to S1, 1 to 2, 2 to 3, and 3 back to 0. But when C is 1, count down, right? Count down 0 to state S3, state S1 to state S0, S2 to state S1, S3 to state S2. And the output of each state, okay, I define S0 is the state that produce output of 0, 0. S1 produce 0, 1. S2 give output of 1, 0, and S3 give output of 1, 1. Okay. From this, so I define the next step is define the value of each state name or do state assignment. Do state assignment. Okay, from this to this. Okay, define the value. After do state assignment, so I think in this case I assign 00 for state is 0, 01 for state is 1, 10 for state is 2, 11 for state is 3. Okay, then I just replace or change the name to its binary code. After that, now I have transition output table. So I know the value of Q1 star, Q0 star when clock tick, right? And if I use D flip-flop, that means I know the value of D1, D2, which is same as Q1 star, D1, D0, which is same of Q1 star and Q0 star. You can copy the table to this one. And this table is show relationship between what? Between D1, D0 and Q1, Q0 and input C, right? So from this one, actually, you know the relationship between output of circuit F, D1, D0, and input C, Q1, Q0, right? Q1, 0 is from flip-flop, feedback from flip-flop, okay? So when you use K-map, you can determine the equation for D1 and D0. For the output also, okay, you can use K-map. So for the example, I you consider D1, right? D1 is 0, 1, 1, 0, and 1, 0, 0, 1. Okay, when you fill in K-map, you will get something like this. This is XOR function. And for D0 is 1, 0, 1, 0, 1, 0, 1, 0 at here when you fill in K-map. So you select this and this, then is Q0 prime. Okay, so you know equation for circuit F, this one and this one. And for output is easy, right? If you consider Z1, actually you need not to write down K-map because there are only two variable, right? Z1 is 1 when Q, same as Q1, right? 0, 0, 1, 1, right? 0, 0, 1, 1. So Z1 is Q1. And for Z0, 0, 1, 0, 1, 0, 1, 0, 1, it's the same. So you can take the signal from Q1 to output Z1 and from Q0 to output Z0 directly. Okay, this is just for example. Okay, for this example, okay, for this example, okay, for this example, the input is from clock, and this circuit let you do frequency divide to produce the output that have lower frequency with 1/3 of clock frequency, namely okay, this period of the output is cover 1, 2, 3 clock. Okay, the period of the output is 3 times of input clock. And if I want the output signal have 50% duty ratio or duty cycle, that means and the duration of low and high must be the same. Okay, now
Sir, can you please repeat again your condition loss again?
the question, right? I want to design frequency divider. Divide by 1/3. For example, if this clock frequency is 30 Hz, the output frequency should be 10 Hz. And more condition, I want the output have got 50% duty ratio, namely high and low period must be the same. Okay, so from this problem, at first I must consider how many states, right? If you note, for this clock period and this one and this one, 1 2 3, right? It's one period of output signal. At the beginning, maybe this to this, the first period, let's call state A. State A output is 0. Okay, and from this to this, it's state B. At state B, when input clock is 1, output is 0. When input is 0, output is 1. Okay, and at state C, this period of clock, output is constant 1. So by this, you know that output is depend on input also, right? It may be changed. It may be changed when input change. For example, input is from clock directly. So for this problem, it should be Muri type state machine, right? Muri. So then I draw the table, transition table. There are 1 2 3 states, right? A, B, C, and this is unused state. Okay, let 0 for state A. That means when clock tick, it go to state B. B is 0 1. When clock tick, change from B to C. When clock tick, change from C to A. Okay, and this one is don't care. And then I just convert this Q star to D. If you use D flip-flop, right? So this is the same value of D1, and this is the same value of D0. Okay, this is D0, this is D1. Anyway, from this you can derive equation for Q1 star or D1, right? With 0 1 0 and don't care, with the same as 0 1 0. Okay, you can define it as Q0, or you may write Kmap, okay, for two variable. And Q0 star 1 0 0, don't care, and it will be 1 when input is 0 0, or you can write Q1 prime and Q0 prime. Okay, so now you get equation. Okay, from this equation you can draw circuit diagram by this. Q0 star and D0 equal to Q0 star, so D0 equal to D1 prime and Q1 prime and Q0 prime. This is Q0 prime, this is Q1 prime, and together and become excitation signal of D0. For D1 equal to Q1 star, which equal to Q0. So Q0 connect to D1. And how about the output? The output, okay, at state A, output is 0. At state B, output is 1 when clock is 0. Output is 0 when clock is 1. And output at state C is 1, constant. And for state 1, 1, that is don't care. So when I use right in KMap, okay, I can determine the equation of output. And then I connect the circuit, follow this output equation. That's all. Understand? Okay. Okay, now I will introduce you some often used module or element in clock synchronous state machine or sequential circuit. Okay, the first one is register. Register actually is composed with multiple bits of flip-flop. For example, all of these use common clock. That means when clock tick, all of these flip-flop will read the data at the same time. For example, if data is 1001, when clock tick, the output of flip-flop will be updated to 1001 at the same time. Okay? Parallelly read the input, or sometimes it's called load. Okay? Load. Okay? You load input value, multiple bit input value at the same time. Okay, this is register. And this is for example, 4-bit register, and this one is 6-bit register. Okay, and the next one is counter. Counter by definition, when you write state diagram, is contain a sequence cycle change of the state. Okay, the normal one is, for example, is binary counter. Okay, it will give the output of binary sequence. For example, for 4-bit binary counter is 000, 0001, 0010, and so on until 111. And when clock tick again, it's back to 00. Okay, this is counter. Node and node. For the counter, the relationship between the present state to the next state, from this state to next state, is add 1, right? Okay, from this to this, when you add 1, it changes from 0001 to 0010. Okay, from this state to this state, you just add 1. Okay, or if you observe that, if you observe this LSB bit, it's change 0101010, right? It's change every clock tick, right? Or toggle every clock tick. But for the next digit, when clock tick 00, when clock tick change 0 to 1, clock tick 11 not change, clock tick change 1 to 0, and so on. Okay, 2 2 2 2. Okay, for the next digit 4041 4041, and the last MSB 8081, right? So if you can determine the timing when the value change, that means you can generate, okay, the sequence of counter. For example, if you consider this digit, it will change or toggle when some condition. When what? When the previous digits of bit are 11, right? Right, are 11. This not 11, not 11, not 11, not change, not change, not change. But when the previous digits all are 11, when clock tick, it change. Why? Because for the next state, okay, the value is increased by 1, right? Okay, when you add 1, if this 1 so some carry out occur at this digit, right? And because of this carry out become carry in for the next digit, so it change the value from 0 to 1, or if digit is 1, then it change to 0. Okay, so by this condition, I can implement the circuit by using this one. For example, okay, for this one is T flip-flop. T flip-flop will change the value for every clock tick. Okay, for every clock tick. So if you observe that this enable is 1, when what? When this bit is 1, this bit is 1, this bit is 1, this bit is 1. So if the previous digit is 1, the flip-flop will toggle or change the value of its value. Okay. For this bit also we change when enable is 1. It will be 1 when this bit is 1. Okay, and so on. This is the counter. In commercial, for example, IC 74163. This is synchronous 4-bit binary counter. Okay, you can use this one as the counter. For the detail, I don't explain. Okay, I just you know that there is a counter that you can use it. Okay, and this is just for example of circuit diagram. Okay, to use this counter. Okay, this is for example of the circuit. You can use it to count. For example, for 4-bit counter, it count from 0000 to 1111. Okay, for binary counter. But if you want to count more, for example, if you want to implement 8-bit counter, you may bring this to 4-bit counter, okay, together, okay, to count. Okay, okay, and the last often used circuit is chip register. For chip register, actually it register, one kind of register, but for register, as I said previously, something like this, right? It read the data, okay, at the same time. But for chip register, just connect the output from this flip-flop to the next one, from this to the next one, from this to the next one. For example, if this input is A, okay, A, this output is B, C, D, and E. When clock tick, every flip-flop will read the data at the same time. Okay, then the flip-flop will read A, right? This before we read B, right? This before we read data of C, and this one you read D. So that means when clock tick, it will update to A, B, C, and D. Okay, A, B, C, and D. So you know it chip, right? Chip the position B at this position, chip to this position. Okay, this is a chip register. Okay, and for this one is just for commercial example of chip register. Okay, now for the detail of this example, because of time, so I will skip, and I want to talk the last topic for today. Okay, it's called ASM. What is ASM? ASM is more one technique to design state machine. Okay, for the previous example, we design by using something like this, right? Write down state output table, and then for the problem, write down the state output table, and then do state assignment, right? After that, find out the equation from this transition table or excitation table, and find output equation. So you can implement the signature circuit. But for some system, it's more complicated. It's not suitable to use the method, something like that. So now let's introduce the sorry. Okay, let okay, I will introduce you more technique to do the design. It's called ASM, or algorithmic state machine. Okay, for this design is similar to do some computer programming to draw something like flow chart, flow chart, sorry, flow chart. Okay, similar way. Okay, let's see the detail. The component of AM's design. You at the beginning, you must draw the AHM chart, which is similar to flow chart. Okay, which composed with state box, decision box, and conditional output box. Okay, let's see the detail. For state box, this one, state box, composed with state name and its binary code. For example, maybe state initial state name is binary code maybe 000, something like that. Or this example is state idle, state code is 00. Okay, for the codes it may be depend on number of state. Okay, for example, if there are 4 state, okay, this binary code may be only 2-bit. And inside this one is register operation. Okay, or output. Okay, output that become active. Decision box, you can write this one or this one, something like this. And some condition, if this condition become true or yes, go to this direction, or if 0, go to this way. For example, this one, if x is 1, go to here, and if y is 1, go to state B. And you can take y first and then x. If y is 1, if x is 1, then go to B. Or you can take x, y at the same time. Because when you take x equal to 1 or not, or y to 1 or not, you use combinational circuit, right, to compare. So before clock tick, before go to the next step, this comparator, which is a combinational circuit, must give the final result, okay, completely before clock tick. So you can do the comparison of x or y first or at the same time, not affect the final result. And for this one is conditional output box. Okay, right in this. Okay, for this one is mean that this value, okay, based on the input condition. This is the input variable. If input start is 1, this register PC will be 0. Okay, all clear. Okay. Okay, let's see this diagram. Okay, for this group, it in the same state. Okay, let's consider this is input start. At the beginning become 0 and then change to 1. And Q0 also one more input. And state, this is state name, state idle, state mount 1, state mount 0. Okay, at the beginning assume it is state idle. Okay, at state idle, the output eval become 1. Okay, it's active. Okay, it's 1. And then now start is 0. Okay, when clock tick, start is 0. So it go to state idle. So still be state idle. Okay, but when start is 1, at this clock tick, start is 1. Register A, this is register A, okay, will update or load the value or assign the new value 0 to A. So now this clock tick, A is load value or clear to 0, 0, 0. And the value of Q0 at this clock tick is 1. So it's go to state mount 1. So state then change from idle to mount 1. Okay? And this state, no eval, mean that output eval become not active or become 0 for the example. Okay? Okay, now for this example, just show you the relationship between normal state diagram and AAM chart. For example, for this one, this is a mirror type state machine. X is input, Z is output. At state A, at state A, at state A, and this is state B, this is state B, this is state C. Because of 3 states, so I use only 2 bits to represent state A, B, and C. If you use flip-flop Q1, Q0, mean that if the value of Q1, Q0 is 0, mean that now the circuit is on state A. If the value of Q1, Q0 is 0, 1, that means the circuit now is on state B, or 1, 1, circuit is on state C. Okay, from this, input X, when at state A, when input X is 1, it's go to B. When X is 1, go to state B. The output, when input is 1, output is 0. So this is output is 0. Okay. And when X is 0, go to A and output is 0. When input X is 0, output is 0 and go to state A. Okay. At state B, when input is 0, go to A, right? Output is 1. At state B, when input X is 0, output is 1 and back to A. When input is 1, output is 0, go to state C. When input X is 1, output is 0, go to state C. Note, the output value may be 1 or 0, depend on the value of X, right? At state B. Okay. So this is mirror type state machine. Okay, mirror type state machine. And at state C, when input is 0, output is 0, go to B. At state C, when clock tick, is go to output is 0, go to state B. And when input X is 1, output is 1, go to A. When input X is 1, output is 1, go to A. Okay? Understand? And for more type state machine, the output in state diagram right in the same circle of the state. And this is the input value X. At state A, output Z is 0. Okay. At state B, output Z is 1. At state C, output Z is 0. Okay, for the state check, at state A, when input X is 0, go to A. At state A, when input X is 0, go to A. But when input X is 1, go to B. At state B, when input X is 0, go to C. For B, X 0, go to C. When X is 1, go to A. At state C, when X is 0, go to B. When X is 1, go to A. Okay? Understand the meaning? So now, let's do this example. Example 2. For example 2, let's design binary divider. X divided by Y by using this algorithm. Let Q is 0 at the beginning, Y x is greater or equal y, x equal to x minus y, and do one increment at q and repeat this, okay, until this condition become false. Then r equal to x. R is remainder, okay. Q is the answer. For example, if I divide 15 by 4, based on this algorithm, Q is 0 at the beginning, right?
Hello, sir. Your connection is down. We cannot hear. So please repeat again.
Okay. Do you hear me clearly now?
Yes, we can.
Okay. Okay. For example, I now I want to do binary division based on this algorithm. For example, if I do division 15 divided by 4 based on this, so now x is 15, right, divided by y is 4. So I compare that x is greater than y or not. If yes, do this one, right? So because 15 is greater or equal than 4, right? True. Then I do this one, x minus y, 15 minus 4. Then it's become what? 11, right? So update to x and then count q, okay? Count q, 0, count up to 1, okay? After that, 11 still be greater than 4, right? So I do uh, this again, minus 4. Then it become what? Become 7, okay? 7 still be greater than 4, so then I minus 4 again, and now it's become 3. Now 3 is not greater uh, than uh, than 4, right? So now compare with 4, right? It's not greater than 4. So you stop this process. So now Q is count up how many times? 1, 2, 3 times, right? Q plus 1, right? Start from 0, then it's become 1 and become 2 at here and become 3 at here. So the answer is 3. Okay, it's 3. Okay, Q is 3. Okay, and the remainder is, for this sample, is 3. Okay, understand? Okay, based on this algorithm, at first I write ASM chart, okay, like this. From this, you should be able to write this one. At state idle, ready signal uh, become true or become 1. Okay, it's 1. To show that now it's ready to do the binary division. And then wait for input start. If start is 0, okay, still be wait at state idle. But when start is 1, okay, go to initial state. To initialize the value of register M, N, and Q. Okay. For this state, okay, it's prepared to load data from X, Y to variable m and n, and 0 to q. Okay, this is initial state. Just wait. Okay, when clock tick, it's go to state wait. Go to state wait. For state wait, do nothing. Okay, just wait. Wait for what? Wait for loading data from uh, x, y to mn and clear value counter q completely. And then compare the value that keep in variable m and n, that this condition is true or not. If yes, go to state process to do subtraction and increase q by 1. And repeat this one. Repeat this one until this condition become false. Go to state finish. Okay, go to state finish, and then when clock tick, change to state idle. From this one, there are 1, 2, 3, 4, 5 states. That means based on this one, you may use at least 3 flip-flop, right? 3 bit of state variable. Anyway, I may reduce number of states. If you consider this state during you wait the start signal, you do not think about this variable, right? So I can move this action to this state. Namely, during wait start, I load data from x, y to variable mn and 0 to q during wait. Okay, so I can reduce or remove this state. Okay. Anyway, from this state, if you consider, if you complete the calculation, your result is in Q, right? And if you complete this, wait at this state, and then when go to this state, what happened? During wait the start signal, the value of Q is cleared to be 0, right? Okay, so the answer from the previous calculation in Q it's very short lifetime. If you don't want Q to be clear at this, so you should add more variable to keep the answer. In this case, I add W to keep the answer. Okay, so from this let's analyze, okay, what kind of component you need to do the machine. Okay, from the behavior of variable m, n, it should be register. Okay, and q at this state is set to be 0, but this state is to 1 increment. So the component for q should be counter, okay, which can count up, okay, and clear. What else? For r, w also register, okay, and for this one you use comparator. Comparator is just one kind of combinational circuit, and this subtraction also is combinational circuit that you need to implement this problem. And if you note that At this state, you assign value of m with x, but this state, the input of m is from subtractor circuit. So what happened? For register m, the input, this state is from x, but this state is from m minus n. You can connect, right? You cannot connect from x or m minus n directly to input m at the same time, right? So you need what? Multiplexer. Okay, you need multiplexer. Okay, so this one. Okay, you need multiplexer to select the data from x or m minus n. At this state, you want to load data from x, right, to register m. So at this state, the value of select should be 0. Okay, and at this state, you want to load data from m minus n. That means select should be 1. Okay. Okay, to do the operation, and for each register, that is load enable. This is control or enable signal. For example, if you want to load data to register n, at this state, load n should be 1. Should be 1. Okay, prepare to load. But not load data. For example, load data from y or read data from y to n suddenly. Don't forget, this is a clock synchronous device. It must wait for clock tick. Okay, must wait for clock tick. At this stage, it just prepare the signal to control. Load signal is 1 at here, and when clock tick, it read data from y and then update register n with value of y. For state idle, register m also at state idle, load m should be 1, and then when clock tick, it read data, right, from this. And at state idle, if select is 1, so data from x will feed to register m. And for counter Q also, okay, at state idle, it should clear, right? So this state clear should be 1. When clock tick, clear is 1, so clear the value of counter to be 0. At state process, for example, at state process, register m, we will load data or read data, right, from m minus n. That means you want to load, right? So the value of load m should be 1 at this state. And select value should be 1 also. To select data from address 1, feed to register m. And the value will be updated again when clock tick. Okay? When clock tick. Okay. Just wait for clock tick, then update the value. Okay? So at this state, again at this state, it's just wait. Right? Apply 1 at here and count up. Okay, this is count up. Counter is 1 at here. Okay, just prepare. But the value still be not changed. It will be changed when clock tick, right? When clock tick. When clock tick, then change to state wait. And at state wait do nothing. That means load m back to 0 and this whole back to 0. Okay, to disable. okay, and keep the value in the counter and register it. After that, when clock tick, prepare the value, okay, of M and N. Prepare, compare the value, prepare the value of M and N, and then at this state, compare the value of M and N, that M is greater or equal N or not. Okay, if yes, go to step process. Okay, if no, go to step finish. At step finish, load data from M to R and from Q to W. That means the output of M must connect to input of register R, and output of counter Q must connect to input of register W. And this state finished. Load R should be 1, load W should be 1. Okay, when clock tick, the register R will read data from M and register W will read data from counter Q. Okay, so this set of circuit is called data path. Okay, you must design this path first. Okay, now,
Hello, sir.
okay,
Yes. In this part, why especially we need multiplexer for using?
because for multiplexer, right?
Yes.
Need for the problem because register M at this state is load data from X, right? Load data from X. But at this state, the same register M, it get a load data from M minus N. Different input, right? Different source of the input from X and from M minus N. This is
Yes.
M minus N. So you need multiplexer. At this state, you select data from address number 0 or from X to input register M. But at this state process, you must change value of selected signal to 1, right? For select data from here to here. Okay?
Okay. Yes.
Okay. Okay, now the problem is where. Okay, now if you understand this data unit or data path, now the problem is how to get the signal, the control signal from for load N, load M, or load R, or clear, or up, or hold, or something like that. You need more circuit, right, to generate this kind of signal. Okay, this part of the circuit is called control unit. Okay, this control unit you generate this kind of enable signal or control signal to each device, including multiplexer, right, to control that you select input from address 0 or address number 1. So you must design control unit also. For control unit, actually, you can design by using the previous one, namely flip-flop and circuit F and circuit G, namely the state machine that I said for the previous topic. Okay, so now to design control unit, actually it's easy if you use this AM chart. Okay, from AM chart and from data path, you can write down the chart for control unit easily. For example, at state idle, at state idle, ready, output ready, active, right? Become 1, so it should be 1 at here. And for M, get data from X. That means load M should be active and select signal. You can write more. Select signal should be 0. Okay, but because it's not active, so I don't like, I didn't write in here. Don't like means it's not active. Okay, it becomes 0. And for N, load data from Y, so load N must be 1 at here also, right? N. Okay, and clear, Q becomes 0, so clear should be 1 at this state. Okay, and for state wait, do nothing. At state process, resist M, load data, right? So load M signal should be 1, and data is come from M minus N. M minus N, that means selector signal should be 1. So select should be 1 at here. And Q plus 1, that means counter should be count up. So signal control count up signal should be 1 at here, at this state. Okay, and for state finish, ready is 1, load R is 1, load W is 1. Okay, okay, for this one, when you get this control unit, so now you can design the state diagram for control unit. For this one, 1, 2, 3, 4, 4 states. Then there are 2 flip-flop. In this case, it's Q1, Q0. Okay, 0 is 4 state idle. 1 is 4 state wait. 0 is 4 state process. 1 is state finish. Okay, now let's consider what is the next state. What is the next state? At state 0 or state idle, it will go to state wait, right? Or 1 when start is 1, and when start is 0, it go to state idle or 0. Okay, understand the meaning? This is the input condition. Okay. That state will change from present state to next state. And for state wait, it will go to state process 1 to 10 when this condition becomes true. If this condition becomes false, it goes to state finish or 1. Okay? And for state process, just wait for clock tick. Go to state wait 10201. No condition. Or it's already true. Okay? And for 11, when clock tick, go to 00. Okay? No any input condition. Just wait for clock tick. Okay, now from this one, okay, now now I will use decoder to generate circuit G from the yesterday lecture, you know, right? Decoder can implement any function, right? For conventional circuit. Okay, I use this one. Okay, this is decoder. At state 00, at state 00, at state 0, output of flip-flop will be 0, 0, 0. Okay, so Y0 will be 1, right? At state 01, 01 Y1 active, right? At state 10 1 1 at T 1 1 0 1 0 Q1 Q0 1 0 1 0 is 2 Y2 active, and at state 1 1 Y3 active. Okay, something like that. Okay, so let's consider, for example, ready, output ready is active at state 0 0 or 1 1, right? Right? So for output ready will be 1 when output of decoder is Y0 or Y3, right? Because Y0 is active when Q1, Q0 is 0 0 and finish is 1 1. Okay, and at state finish, okay, Q1, Q0 is 1 1. Okay, and for load M active at state 0 0 or 1 0. 0 0 or 1 0, load M 0 0 is Y0, 1 0 is Y2. Okay, and for load N, only this state. Okay, so this state, load N active, clear active. What else? Select. Okay, it's 1 at here, state Y2, state process. Okay, Y2 active. Okay, this is circuit E using decoder. And for circuit F, this one, circuit F. For circuit F, I use multiplexer to implement. You know, right? Multiplexer can you can implement any combinational circuit by using multiplexer. Okay, for multiplexer, okay, let's consider this one. I use Q1, Q0 as selector signal. Okay, from this table, Q1 star or the same value of D1 at state 0 0, namely when Q1, Q0 is 0 0, the value of Q0 star or VBD1 is 0, right? So you feed 0 at here. Okay, and for state 0 1, namely when this one is 0 1, and data of Q1 star should be 1, so I feed 1 at here. And for state 1 0, when Q1 is 1, Q0 is 0. Okay, it read data from address 1 0, right? And the value of Q1 is 0, so you feed 0 at here. Similarly, for state 1 1, it should be 0, so apply 0 at here. Okay, and for Q0 star, which from D0, for this one, for state 0 0, okay, 0 1 0, same value of start, right? So apply start at here. And what else? 1 0, 1 0 is opposite to this one, so invert of comparator. M greater than or equal N. As this state is constant 1 at here, and state and value of Q0 star is constant 0, so apply 0 at here. Then finish. Okay, for this control unit. So you just connect this, and you just connect this signal to this data unit. Okay, this kind of signal. Then you can complete state machine by using this ASM. Okay, that's all for today.